When we drop a raw foundational model into a production network, we introduce a severe operational hazard. Continuous text generation is entirely unpredictable. Applied directly to software engineering, unbounded text generation fails. An autonomous agent cannot execute raw text. Without tight execution pathways, a model hallucinates commands, overwrites critical files, and operates without any governing boundaries. This is the problem kilocode version 7.4 solves. The engineering team stripped away the legacy, monolithic extension scripts that implicitly ran these models. In their place, they built a structured, orchestrating runtime. The architecture rests on a specific equation. A functioning agent is the sum of its foundational model and its operational harness. A reliable production agent does not emerge from model intelligence alone. It depends entirely on the mechanical rigor of the runtime built around it. To understand how this control layer functions, we will dissect kilocode's migration to a durable, event-sourced service graph runner. This diagram maps the core orchestrator of the entire explicit control architecture. Kilocode calls this the session runner. It replaces open-ended, implicit feedback loops with predictable, explicit state machines. Every input and output must travel along these predefined paths. To function, the session runner populates these pathways with specific operational primitives. It requires defined tools, strict permissions, structured memory, and absolute loop control. By routing every action through this centralized hub, the system converts a chaotic, continuous stream of language into a highly structured operational contract. This block diagram shows the act, observe, and continue loop. It starts with the assembly phase, gathering the request and context. Next, the model receives context, streams reasoning, and proposes tools. These proposals hit the control gate, which evaluates each action before cycling back. The loop enforces explicit stop conditions to maintain absolute control. If the model proposes no tools, if a step limit triggers, or if a user rejects an action, the session runner terminates. A traditional chat interface leaves the model open-ended and constantly waiting. Kilocode instead serializes the entire process into rigidly gated increments. Forcing execution through this act, observe, and continue loop creates a repeatable runtime environment. The agent moves only when permitted, step by step. Engineering teams often assume that granting an agent access to more tools automatically increases its capability. In production, the logic is inverted. A broader callable surface increases tool selection errors and heavily thins the established trust boundaries between the foundational model and the operating system. This schematic details the tool registry pipeline. Acting as a gatekeeper, it defines exactly which tools the model sees. During materialization, policy filters actively hide disallowed tools. If a task doesn't require editing, the edit tool is completely removed. The registry also handles dynamic injection. When external capabilities are required, predefined skills and model context protocol interfaces are injected directly into the approved tool subset. Once the model selects a tool, the action enters the settlement flow. The system stages the tool, pulling it entirely out of the text stream to enforce strict authorization checks prior to any execution. Because the tool registry filters the available list before the provider turn, the model cannot hallucinate the usage of a tool it lacks permission to see. Schema-driven, explicitly materialized tooling absolutely locks down the operational scope, ensuring the agent only interacts with a completely vetted, restricted environment. The host-bound bash command tool represents the highest risk primitive. Executing arbitrary terminal commands on a host machine requires absolute isolation and strict boundaries. This decision tree maps the policy engine. Every settled tool call routes here before touching the host system. Using first match precedence, the payload evaluates against rules that immediately allow, explicitly deny, or divert to an ask state. When a tool hits an ask rule, it triggers a human-in-the-loop fallback mechanism. The run halts entirely. Uncertain or high-risk operations sit frozen in memory until an engineer manually approves execution. If safe but repetitive, operators can persist manual approvals. The system converts a single approval into a permanent always rule for future sessions, speeding up execution without bypassing the engine. This permission-first firewall intercepts and neutralizes destructive operational intent long before the actual host machine ever receives the command. Autonomous software engineering requires intensely prolonged sessions. Over hundreds of turns, models experience context saturation, losing track of initial instructions as the prompt fills entirely with terminal outputs and file reads. Merely increasing the raw token limit of the provider only delays the inevitable failure. It does not solve the underlying need for state continuity. This horizontal timeline illustrates the solution: a two-tier memory architecture to prevent context collapse. The top tier utilizes context compaction. As session data grows, the system compresses older, elongated blocks into highly dense squares labeled anchored summaries. Compaction acts as an anchor for the ongoing session. It ensures the agent retains its core operating instructions, no matter how many files it opens. The second tier provides durable recall. It leverages dedicated memory tools to write crucial findings directly to a stable, external database. This project-scoped, long-term database exists entirely outside the volatile, short-term session state. It survives even if the agent is completely restarted. The model can autonomously query this durable memory, reading its own past notes to bridge complex architectural decisions across entirely independent sessions. Context compaction keeps the immediate thought process clear, while durable recall preserves the global project state. Together, they maintain structural coherence. True session continuity cannot rely on an LLM's raw context window. It must be explicitly engineered outside the model to achieve operable scale. While kilocode effectively solves system state and operational safety, the current architecture fundamentally cannot guarantee code correctness on its own. It relies on model self-completion. A critical architectural component is missing from the core loop: an automated in-loop verification gate. This graph highlights that absence. There is no built-in linting, automated testing, or greater evaluation looping inside the turn path to verify a file edit. The architecture pushes this burden outward. Correctness checks are offloaded to external host sandboxes and human QA processes. Infrastructure engineers must therefore enforce strict operational policy and configure their deployment environments to handle the verification the harness currently skips. Standard foundational models are built for rapid sequential text generation, but that output only becomes governable through the application of explicit, rigorous control planes. A production-grade agent is defined entirely by the boundaries, tools, and permissions of its operational harness, not the raw intelligence of its core.